Okay, so in this lecture, we are going to look at ARMA random processes, which is a fifth lecture in the sequence. So, auto, regressive, moving, average, random process. So, how do we go about this? Initially, we saw AR separately and MA separately. Here, we are going to see all together. So my x of n will be the original equation number 1 which I started with, comprising of both the negative and the positive terms. So this would be x of n equal to summation k equals 1 to p ak x of n minus k plus summation k equal to 0 to q bk w of n minus k for all n greater than equal to 0. Here W of n is a white stationary process. So my W of n is a white stationary process. By now you should have got very comfortable with this. So if this is white stationary process, one more additional thing is its mean equal to 0. So E of W of n is also equal to 0 for all n greater than or equal to 0. And its variance will now become sigma squared, and sigma squared is E of x squared minus E of x the whole squared. In this case mean is 0, so second term does not exist, and we have E of W squared of n, and this is true for all n greater than or equal to 0. Now we move along to find the mean, variance and autocorrelation function of the ARMA process. So mean of our ARMA process, right? So to find mean, I need to take expectation of my x of n, and this is nothing but minus summation k equals 1 to p, ak comes out, I have E of x of n minus k plus summation k equal to 0 to q bk E of w of n minus k. These will be the two terms which I will be having for all n greater than equal to 0. Now we know that E of w of n minus k, this value is 0 for all n greater than or equal to 0. Hence, my E of x of n reduces to minus summation. I will have k equal to 1 to p ak w of w term will not exist, rather I will just have this expectation of x of n minus k for all n greater than or equal to 0. Since all the initial conditions are assumed to be 0, k equal to 0, so E of w of n is 0 for all n greater than or equal to 0. So this will be our mean. Next, we need to find the variance of the ARMA process. So the variance is now given by sigma squared of n. Now clearly the mean is 0 for all n, then the variance can be written in terms of the autocorrelation function. It can be written in terms of the autocorrelation function. Okay, let us say that it is evaluated at time indices n. Then I will have sigma squared of n, and my sigma squared of n equal to E of, I will have x squared of n, which is nothing but our rxx of n comma n, and this value we will try computing. So my sigma squared of n is now equal to minus summation k equal to 1 to p ak expectation of x of n minus k into x of n minus summation, I have k equal to 0 to q bk expectation of w of n minus k into x of n. So this would result in my sigma squared of n equal to, I will have minus summation k equals 1 to p, I will have an ak into the autocorrelation function rxx of n comma n minus k plus summation k equal to 0 to q bk expectation of, I will have expectation of w of n minus k expectation of w of n minus k into x of n. Okay, so now please, this has to be plus. So this would be sigma k equal to 0 to q bk e of w n minus k into x of n. Therefore, this function gives me minus summation k equals to 1 to p ak rxx of n comma n minus k plus summation k equal to 0 to q bk, I have a cross correlation over here rxw of n comma n minus k. Thus, the variance is the weighted sum of the autocorrelation function evaluated at different times and the weighted sum of the various cross correlations at different times. So, this is the expression that we are getting for variance. Next, let us move on to finding the autocorrelation function of the ARMA process. So autocorrelation function of my ARMA process. Right. Now how to find this autocorrelation function? Autocorrelation goes through a transient period since the signal starts at 0 with 0 initial conditions. This assumption we have been keeping through right from the beginning. Now let us assume that n is greater than p. Then my rxx of n comma n minus 1 is nothing but expectation of x of n into x of n minus 1. Try evaluating this. So this will give me my rxx of n comma n minus 1 will be equal to minus summation k equal to 1 to p. I will have e of, I will have e of x of n minus k into x of n minus 1 plus I have summation k equal to 0 to q bk expectation of, I will have w of n minus k into x of n minus 1. Now consider this is nothing but minus, I will have summation k equal to 1 to p rxx autocorrelation of n minus 1 comma n minus k, and I have a constant term which I missed over here, it is ak, so I will also have that ak plus I will have summation k equal to 0 to q bk, and the cross correlation function, will it be possible to write the cross correlation function directly? No. So k equal to 0 to q bk, let me retain this like this, e of w of n minus k into x of n minus 1. So this would be the autocorrelation function. Now let us consider x of n minus j in the range j equal to 2 to p. When we go for this assumption, we will be getting rxx of n comma n minus j be equal to minus summation k equal to 1 to p. I will have ak rxx of n minus j comma n minus k plus summation k equal to 0 to q bk into expectation of w of n minus k into x of n minus j, where my j runs from 2 to p. So thus in this small illustration we have now seen how to obtain the mean, variance, and the autocorrelation function of an autoregressive moving average process. Since we have already given you example sums separately for moving average and the AR process, autoregressive process, I suppose being higher level students, you can also venture into finding more examples and explore more into the theoretical concept explained in this lecture. Thank you.